Welcome to the deep dive. Today, we're jumping into the data plane development kit.
That's right. We're looking specifically at the Programmer's Guide Release 2.0.0.
And our mission really is to pull out the key ideas, the stuff you need to know to understand how DPDK gets such, well, frankly, amazing network performance.
Exactly. We're digging into the libraries, the functions, but mostly the why. Why is it so fast? What are the core engineering tricks?
And the thing that jumps out immediately, right from the start, is why DPDK exists. It's all about performance by doing things differently.
Completely differently. It throws out the old way the kernel handles network packets.
Bypassing the kernel, avoiding interrupts, using polling instead. Okay, let's unpack that. What does that really mean for speed? Is it just a bit faster?
Oh, it's way more than a bit faster. It's a fundamental shift. Think about standard networking. Packet comes in, NIC interrupts the CPU.
Right. The CPU stops, saves state, switches to kernel mode, does its thing, switches back.
Exactly. All that context switching, it adds up. Huge latency, eats CPU cycles. DPDK just sidesteps all of that.
So no waiting for the interrupt knock on the door. DPDK is just constantly looking, like checking the mail slot every second.
Pretty much, yeah. It actively pulls the network card. Anything new, anything new.
Yeah.
That constant checking is the key.
And how does that translate to speed? Just cutting out the interrupt overhead.
That's a huge part of it. Latency drops massively.
Yeah.
You can just process packets way, way faster, higher throughput.
But there's a trade-off, right? That polling uses CPU.
Definitely. That core is busy, spinning, checking the NIC, even if no packets are coming in. So you dedicate a core, essentially, to get that speed.
Okay, a conscious trade. Power for performance. So moving away from the kernel means you need a new way to talk to the hardware. Memory.
Precisely. And that's where the EEL comes in the environment abstraction layer. It's the bedrock.
The foundation that makes user-space networking possible.
Yep. It gives DPDK apps a standard way to get at low-level stuff hardware. Memory doesn't matter what OS you're on, mostly.
So in Linux, how does it work? The guide mentions thread, sys for PCI info.
Right. It uses P6 threads, reads PCI device info from sys, and crucially, it grabs memory using huge pages.
Ah, huge pages. We hear about those a lot for performance. Why are they so vital here? Is it all about the TLB?
The translation look-aside buffer, yeah, that's a huge part of it. Your CPU cache is virtual to physical address translations in the TLB.
To speed up memory access.
Right, but with standard, small 4 KB pages, you're handling millions of packets, your TLB cache is just constantly getting thrashed. Lots of misses.
And miss means the CPU has to go look it up in the main page tables, which is slow.
Very slow, relatively speaking.
Sure.
Huge pages like 2 MB or even 1 GB mean way fewer entries in the TLD needed to cover the same amount of memory.
So fewer misses. Much faster memory access for packet data. Got it. Like having a map with fewer, bigger regions instead of tons of tiny streets.
Good analogy, yeah. And the EEL isn't just memory, is it? It handles CPU cores, too.
Correct. Core affinity deciding which CPU core runs which DPDK thread. Super important for performance, avoids cores stepping on each other's toes, cache-wise.
And it manages allocating that memory, specifically those huge pages from this system. Yep, carves out those big chunks. And it also gives you a way to get time, like using the CPU's timestamp counter, the TSC, or maybe the kernel's HPT API.
And the starting pistol for all this is SFRDL in it. That's the first thing you call.
That's the one. It kicks everything off, initializes the ELL, sets up memory, scans the PCI bus for NICs, creates the worker threads using thread, the whole bootstrap.
The guide mentions memory zones, backed by huge pages, and contrasts that with Artemalec. What's the deal there?
Okay, so memory zones let you reserve named chunks of huge page memory, and importantly, you know the physical address.
Ah, physical address access.
Right, which you might need if you're setting up, say, DMA directly with a network card. Artemalec also uses huge pages, but it gives you a virtual address, like normal malloc, just backed by faster memory. You don't typically get the physical address with Artemalec.
So Artemalec for general use, memory zones when you need to talk directly to hardware addresses.
Pretty much, yeah.
And the EAL also handles finding the NICs on the PCI bus through sys again.
Yes, it scans syspubs to find compatible devices. Then it uses kernel modules like YOPS generic or the DPDK-specific IGWIO to basically map the NIC's hardware resources directly into the application's address space.
Bypassing the kernel driver entirely.
That's the magic. Direct hardware access from user space.
Okay, ELL sets the stage. What are the next building blocks? How do we actually manage memory and pass packets between cores efficiently?
2 really core libraries there. LibreToMalloc for memory allocation and Liberator for lockless queues.
We touched on LibreToMalloc using huge pages. Why is that better than just malloc from the standard heap beyond the TLB thing?
Well, besides TLB, it really helps with memory fragmentation. When you're allocating and freeing millions of tiny packet buffers constantly, the regular heap can get really fragmented and slow.
Right, finding contiguous space becomes hard.
Exactly. Liber2Malloc uses these big, pre-allocated huge page pools, so fragmentation is much less of an issue. Plus, allocation and freeing can often be faster because it might bypass some kernel overhead. Locality is often better, too, for cache performance.
Okay, makes sense. Now, liberding. Lockless, multi-producer, multi-consumer FIFO. That sounds essential for multi-core.
Oh, it's absolutely vital. Think about getting packets from one CPU core to another.
Yeah.
Normally, you'd need a lock to protect the queue data structure.
Which adds overhead, contention, slows things down.
Terribly so. At these
Yeah.
speeds, liberding avoids locks completely. It uses atomic CPU instructions, specifically compare and swap, CAS.
CAS.
Okay.
Allows multiple cores to enqueue and dequeue items simultaneously without corrupting the queue.
Exactly. Lock-free, super fast, designed for high throughput, especially good for bulk operations, too.
Bulk operation, so moving chunks of packets at once.
Yeah, instead of enqueuing or dequeuing one packet pointer at a time, the API lets you do, say, 32 or 64 at once. Much lower overhead per packet that way. The guide has diagrams showing the different producer-consumer scenarios, figures 5.4 to 5.9, I think.
And the superfast ring isn't just for general core-to-core chat, is it? It's used elsewhere.
Absolutely. It's the engine inside the memory pool manager, Liberd Mempool.
Ah, okay. Tell me about LibreMempool, managing pools of fixed-size objects. Why fixed size?
Again, performance and predictability. Pre-allocating a pool of identical objects like packet buffers means allocation and deallocation is incredibly fast. Basically just grabbing an item from a free list, often managed by that internal libering.
No complex searching for a right-size block like in general-purpose allocators?
None of that. And it avoids fragmentation. Plus, it enables clever tricks, like interleaving packet headers. The guide shows this, figure 6.1, 6.2. You arrange the start of the packet buffers in memory so that consecutive packet headers land in different memory channels or ranks.
Spreading the load across the memory system.
Exactly. So when your CPU cores are processing packets, especially doing L3 lookups that hit the start of the packet, they're less likely to bottleneck on a single memory channel. Better cache usage, better memory bandwidth. It's about thinking how the hardware works.
Very clever. And does Mempool have other tricks?
Yeah, it often uses a per-core cache. Each CPU core keeps a small, private stash of free buffers.
So it doesn't always have to go back to the main shared pool ring.
Right. It tries the local cache first.
Right.
Much faster, reduces contention on that central ring,
Yeah.
only goes back to the main pool if the local cache is empty, or pushes excess buffers back if the cache gets full.
Nice optimization. Okay, we have fast memory pools. How do we represent the actual packets? That's OTRMBUF, right?
Correct. The RUMBUF structure, think of it as the standard container for network packets, or really any message data, moving through a DPDK system.
And it can handle big packets, jumbo frames.
Yep. And a buff points to a segment of memory holding packet data. For packets larger than one segment, you can chain buffs together. Figures 7.1 and 7.2 in the guide show this.
Like a linked list of buffers for one big packet.
Essentially, yes. And critically, each umbuff has headroom.
Headroom. Ah, space at the beginning of the buffer.
Exactly. Empty space before the actual packet data starts.
Yeah.
So if you need to add new protocol headers, like encapsulating the packet, you can often just prepend them in the headroom without needing to copy the whole packet to a new, larger buffer.
Very efficient.
Yeah.
Saves a lot of data copying. And these umbuffs come from LibreMempool.
Yes, they're allocated from those mempools we just discussed, so they automatically benefit from things like the header interleaving for cache performance. There are specific init functions like architect tambuf init to set them up correctly.
What kind of info does an umbuff carry besides the packet data pointer?
Important metadata, like which network port it came in on, the total packet length, how many segments are in the chain, stuff like that. Crucial for processing decisions.
And hardware offload flags.
Right. Flags to indicate if the NIC has already done things like calculate the IP checksum, PKTXX, IPCKSUM, for example.
Yeah.
The application can check these flags and potentially skip doing that work in software.
Saves CPU cycles. The guide also mentioned direct versus indirect buffs.
Yeah. A direct umbuff owns its data buffer. An indirect umbuff points to the data buffer of another umbuff, usually a direct one.
Why would you do that?
It's great for things like packet duplication or fragmentation. If you need to send the same packet out 2 ports or break a packet into fragments, you can create indirect umbuffs that just point to the original data or parts of it. No need to copy the actual payload. Saves memory and time.
Clever. Memory efficiency. And there's a debug mode.
Yep, configured buff debug. If you build with that, the library adds extra checks. Sanity checks on allocation, frame manipulation, helps catch bugs like buffer overflows, use after-free, double freeze, that kind of thing. Can slow things down a bit, but useful during development.
Definitely. Okay, packets represented in debuffs, allocated efficiently. How do we actually shovel these packets between the application and the NIC at light speed? That's the PMD's job. Pulmo driver.
That's the one. The PMD is the user space driver for the network card. It provides the APIs to configure the NIC, its queues, and most importantly, to directly read and write packet descriptors from the NIC's memory rings.
Directly accessing the NIC's RX and TX descriptor rings in memory, bypassing the kernel's interrupt system entirely.
That's the absolute core of DPDK's I/O performance. No interrupts, just pulling those rings.
So the application using the PMD is constantly asking the NIC, got any received packets by checking the RX ring, and got space to send packets by checking the TX ring.
Exactly. And the guide describes two main ways to structure your application around this polling.
Oh, yeah.
Run to completion and pipeline.
Run to completion sounds simple. One core grabs a packet, does everything to it, sends it out.
Pretty much. A core pulls an RX queue, gets a packet or a burst of packets, processes it completely, parsing, lookups, modification, whatever, and then puts it on a TX queue, all in a tight loop on that one core. Simple, low latency for that packet.
And pipeline, spreading the work.
Right. You break the processing into stages. Maybe one core or set of cores just does RX, puts packets onto a liberator ring. Another core dequeues does L3 lookup, on queues to another ring. A third core dequeues applies firewall rules, on queues to a TX cores ring.
Using those fast, lockless rings for handoffs allows more complex processing, potentially higher total throughput.
Can do, yeah. Better parallelism. The guide stresses that the PMD itself should be lean. The policy, the complex logic that lives in your application, not the driver. The PMD's job is just fast I/O.
I saw a mention of limits on how many packets you pull for at once.
Yeah, the RX and TX functions usually take a parameter for the maximum number of packets in a burst, here G32. It's a tuning knob. Bigger bursts can give higher throughput, but might slightly increase latency for the first packet in the burst. Smaller bursts might lower latency, but have more overhead per packet.
Application tunes it based on needs. Makes sense. And the rule about not sharing NIC queues between cores. One RX queue per core, one TX queue per core.
Crucial rule. If multiple cores try to pull the same RX queue or write to the same TX queue simultaneously, you need locks to protect the queue pointers and data structures.
And locks kill performance at this scale.
Exactly. So you dedicate queues to cores. Modern NICs have lots of queues specifically for this reason to support multi-core processing lock-free.
How does DPDK actually know which NIC is which?
It uses the PCI, identifiers the bus, device, function numbers, finds the cards, then assigns its own logical port IDs, DA0, 1, 2. And interestingly, DPDK apps can often configure NIC features directly by writing to the NIC's PCI registers via the EAL.
Wow, really low-level control. Powerful, but maybe needs care. Okay, core packet path covered. The guide then goes into a bunch of other libraries for more advanced stuff. Quick tour. IVSMEM.
IVSMEM, that's for fast, zero-copy sharing between virtual machines on the same host. Uses QEMU's shared memory feature, but backed by DPDK. Huge pages for speed. Good for VM to VM communication without going through the host network stack. Thread safety is important there.
Link bonding, like teaming NICs.
Yep. Aggregate multiple NICs into one logical link. For more bandwidth or for failover active backup, load balancing modes, that sort of thing. Handles link status changes.
Timer library.
High-precision timers for scheduling future function calls. Runs callbacks asynchronously. Can use HPET or the CPU's TSC for the time source. Uses a skipless data structure internally, apparently, for efficiency.
Hash library for lookup.
Exactly. Fast hash table implementation. You give it keys like packet header fields. It gives you back associated data. Highly configurable hash functions, bucket structures. Essential for things like full classification.
LPM and LPM6. Longest prefix match.
Right. For IP routing lookups. Super fast algorithms for finding the best route match in a large routing table for both IPv4, LPM, and IPv6, LPM6. Uses special table structures, TBL24, TBL8, for speed.
Packet distributor. Spreading packets to workers.
Yeah, it takes incoming packets and distributes them fairly across multiple worker cores. Can optionally work with a reorder library to make sure packets from the same flow stay in order, even if processed by different workers.
IP fragmentation and reassembly. Does what it says on the tin.
Pretty much. Handles breaking big IP packets into fragments for sending and putting received fragments back together. Uses those direct and indirect debuffs we talked about.
Multi-process support, running DPDK apps as separate processes.
Yeah, you can have a primary process that initializes things and secondary processes that attach to the shared huge page memory set up by the primary. They can communicate using rings, good for scaling across new MA nodes or just structuring large apps, but watch out for things like ASLR complications.
KNI kernel NIC interface sounds like a bridge back to the kernel.
It is. KNI creates a virtual network interface in Linux that's connected to your user space DPDK application. Packets sent to the KNI interface in the kernel get passed down as umbuffs to your DPDK app. Your app can send packets up to the kernel via KNI too, converting dumb-buffs to kernel scuffs.
So you can still use standard Linux tools like TCP dump or ifconfig on that KNI interface, or interact with the kernel's routing table.
Exactly. Lets your fast DPDK path coexist and interact with the normal Linux networking stack when needed. Useful for control plane traffic.
Thread safety, obviously important. What's the general guideline?
It varies by library. Core stuff like libretering, libmempool are designed to be lockless and thread-safe for their main data path operations. Things like PMD RxCX functions are safe if you follow the 1 queue per core rule. Setup APIs, configuration APIs might not be thread-safe and need external locking if called concurrently. You really need to check the docs for each function you use in a multi-threaded context.
Okay, check the docs. Lastly, QoS framework, quality of service.
Provides building blocks for traffic management. Things like policers, rate limiting, droppers like red for congestion control, and a hierarchical scheduler.
Hierarchical?
Yeah, typically a multi-level structure like port, support, pipe, traffic class, queue, allowing you to apply different bandwidth guarantees or priorities at different levels. Often uses weighted round-robin WR scheduling.
Wow, that's a lot of tools in the toolbox. The guide also talks about a packet framework. Sounds like a higher level thing for building pipelines.
It is. It's an abstraction layer on top of many of these libraries, designed to make building complex packet processing applications easier and more structured.
How does it work? What are the concepts?
You define pipelines as connections between ports, input, output, and tables. Packets flow into an input port, get processed by one or more tables, and eventually exit an output port or get dropped.
And tables do the actual work, like lookups.
Right. There are different table types built in. Hash tables, using libhash, LPM tables, librel tables, ACL tables, even simple array lookup tables, or tables connected by software rings, libdaring. Each table performs some lookup or action based on the packet.
The hash table implementation sounded quite detailed in the outline.
Yeah, the framework's hash table has specific optimizations mentioned, like different bucket types, fixed, extendable, and a pipeline search process designed to work well with CPU caches and prefetching. Lots of figures showing that, 24.2 to 24.7.
So you define the graph, basically. Packet comes in here, goes to hash table if match, goes to LPM table if no match, goes to output port X.
Exactly that. You define the connectivity. Table entries usually specify the next hop action, go to another table, send to port, drop, etc. Ports and tables can also have action handlers for custom code execution.
Seems very modular. Does it support different processing models?
Yes, you can implement pure pipelines, or stages that act more like run to completion, or mix them. It also has considerations for multi-threading within the pipeline, managing shared data, maybe using locks or message passing, and hooks for potentially offloading parts of the pipeline to hardware accelerators.
And vhost fits in here too, for VMs.
Right, the vhost library lets you plug virtual machine interfaces, like VirtuoNet, directly into these packet framework pipelines. So VMs get near-native network performance via DPDK, bypassing the host kernel. Uses host user typically for best performance.
Okay, shifting gears slightly, the guide finishes with building and optimizing. Any key practical tips jump out?
Yeah, covers the basics like the directory structure, how to use the make files to build DPDK itself in your own apps against it.
Yeah.
But the performance tips are crucial. Things we've touched on. Really favor run to completion if latency is critical. Always process packets in bursts, bulk API. Huge performance difference. Be super aware of memory access patterns. New MA locality is critical. Try to keep data on the same in-MA node as the CPU core processing it. Think about memory channels. Minimize cache misses.
And things like branch prediction.
Yeah, try to structure code, especially in the tight loops, to be predictable for the CPU's branch predictor. And definitely compile targeting your specific CPU microarchitecture, now March native or similar, to let the compiler use the best instructions.
So it's not just about using the DPDK libraries, it's about how you structure your code and think about the hardware underneath.
Absolutely. The programmer's guide gives you the tools, but understanding the why behind them, the kernel bypass, the polling, the lockless design, the memory optimizations, is key to using them effectively.
It really paints a full picture, from the EL touching the hardware right up to high-level frameworks and optimization tips.
It really does. It shows how DPDK systematically tackles every potential bottleneck in the traditional network stack.
For me, digging into this, the real aha moment is seeing how all these pieces fit together. The EAL enabling user space access, the mempools and buffs managing data efficiently, the rings providing fast intercore comms, the PMDs doing the interrupt-free I/O. It's the combination that unlocks that performance.
It's a complete rethinking, driven purely by the need for speed.
Which really makes you think, with this kind of speed possible, what does that mean for the future? For cloud networking, for NFV, for crazy real-time applications we haven't even thought of yet? What new doors does this kind of performance actually open up?
That's a big question, isn't it? It changes the assumptions about what's possible with network processing. A fascinating place to be.